All right, well, day one of our trig identities unit, and we're looking at solving trigonometric equations algebraically today. So this is just an extension of things that we have already done in our previous unit. Okay, a little bit more challenging, but we can handle it. Okay, so to begin, why don't we just remind ourselves of our special triangles. So the special triangles help us to remember the trig ratios of special angles like 45 degrees or 30 degrees, 60 degrees. So let's fill this in. 45 degrees, a reminder to us in radians, this is pi over 4 radians. Okay, so this 45 degree angle we can also think about as being pi over 4 radians. And so the side lengths of this special triangle, it's an isosceles right triangle. So sides opposite equal angles are equal. So we've got side lengths of 1, 1, and then by Pythagoras, the square root of 2. Okay, 30 degrees is pi over 6 radians. And 60 degrees is pi over 3 radians. So we'll fill that in as well. This is pi over 3. This is pi over 6. And then we've got side lengths of 1, 2, and the square root of 3. Okay, so we'll keep that in mind. A few other points to note. So when solving an equation, we need to find all the values within the given domain. Okay, so important point to note, and here's what we're talking about here. So solve for the value or values of x that are in the domain 0 to 2 pi. And the reason we state that domain is because we know that the sine of x, the cosine of x, these are continuous functions. Okay, they've got a domain of all real numbers. And so really there's an infinite number of solutions until we restrict that domain. So find the solutions within the domain 0 to 2 pi. Okay, the other thing that we want to keep in mind, and this is probably something relatively new, but each value of sine and cosine, except for 1 and -1, occurs twice within one cycle or one period. Okay, so this is really important as we move forward in this unit. And I'm just going to give you a diagram of what that's talking about. So I'm going to draw one period of our basic sine function, and I'll draw one period of our basic cosine function. So think about this here as being one period of the sine of x. Okay, so max value of 1, min value of -1, the period is 2 pi. We have all of our significant points, so midpoints, max points, min points. They all occur every quarter period. Sine starts at a mid and increases to begin. And this is generally what it looks like. Okay, our sine curve. Okay, so the note here is each value of sine and cosine, except for 1 and -1, occurs twice within one period of the function. Okay, so think about the y coordinates here. These are the values we're talking about. Let's take 1/2, for example, and I'll just grab another color here. So this function is equal to 1/2 exactly 2 times within one period. So approximately right there and approximately right there, but nowhere else. Okay, it's equal to 0 exactly 2 times. Here and here. Now this doesn't count at 2 pi, and that doesn't count because if you look closely at the domain, okay, 2 pi is not included in that domain. Okay, now the exceptions, of course, are 1 and -1. Okay, so the sine of x is equal to 1 just the one time. It's right there at pi over 2. And the sine of x is equal to -1 only one time, and that's at 3 pi over 2. Okay, but every other value between -1 and 1 occurs twice. Okay, the other thing to note here is that the sine of x is never equal to a value greater than 1. Okay, so the sine of x is never equal to 2, it's never equal to 1.5, it's never equal to 100. And the sine of x is never equal to a value that is less than -1. Okay, so it's never equal to -2 or -1.5, -100. There are no solutions for that equation, and we'll keep that in mind as we go through today's notes. Okay, so a bit of review to begin. Solve for x within the domain 0 to 2 pi. And the first one is the sine of x is equal to 1/2. So 1/2 is our sine ratio, and we are looking for x, the x which represents the unknown angle or angles that have a ratio of 1/2. Now, what does the 1/2 tell us? That's a positive ratio, and so we know that sine is positive in quadrants 1 and quadrant 2. Okay, so this angle right here in standard position and this angle right here have positive sine ratios, and we're going to say that that sine ratio is 1/2. The other thing that we know about this is that both of these angles have the same reference angle. Okay, so we're going to use that reference angle to find those missing angles. Okay, so I am going to use our special triangles that we have above here, and we've got a special triangle containing side lengths of 1 and 2. Now, sine is the ratio of the opposite side length divided by the hypotenuse side length. So we're looking for an angle that has an opposite of 1, a hypotenuse of 2, and that's the angle at the top there, pi over 6. Okay, so I'm going to jot this down here. This is our reference angle. Our reference angle is pi over 6, and we'll use that to find what I will call theta 1 and theta 2. Okay, that's the angle that exists in quadrant 1 and the angle that exists in quadrant 2. Now, the angle in quadrant 1 is going to be the same as the reference angle, so it is pi over 6. And then the angle in quadrant 2, we're going to take pi, or we could actually think about it as being 6 pi over 6, and we will subtract the reference angle of pi over 6 to get 5 pi over 6. Okay, so these are our two solutions here, 5 pi over 6 and pi over 6. Okay, same idea with number 2. So we've got a cosine ratio of 1 over the square root of 2. That's a positive ratio. And I'll just do this over here. So all suckers take chemistry, or all students take calculus. So that reminds us that in quadrant 1 and 4, we have positive cosine ratios. Okay, so those two angles have positive ratios, and they have the same reference angle. So those two red dots represent the reference angle. Now, cosine is the ratio of the adjacent side length divided by the hypotenuse side length. So we're going to look for that adjacent 1 hypotenuse root 2. We have a reference angle of pi over 4. Okay, so I'll just jot that down. That is theta r. And we're going to use the reference angle to find theta 1 and theta 4. Okay, so theta 1 will be the same as the reference angle. It's going to be pi over 4. And theta 4, we're going to do 2 pi minus the reference angle. So we can think about 2 pi here as being 8 pi over 4 minus pi over 4. We get 7 pi over 4. And those are our solutions. Okay, next one, this is a little bit more challenging. Okay, so our sine ratio is -2 over 5. Now, those are not side lengths of a special triangle, okay, which is okay. But we're going to need our calculators here. So if you haven't got a calculator handy, take it out. What I want to keep in mind, though, is that this is a negative sine ratio. So sine is positive in quadrants 1 and 2, and it's negative in quadrants 3 and 4. So we're looking for this angle here and this angle here. And again, they share the same reference angle. Now, how can we find that reference angle, theta r? We're going to use some of our Math 10 trig. So I am going to do the inverse sine of, and I'm not going to do the inverse sine of negative 2 over 5. All that negative is telling us is in which quadrant these angles exist. Remember, the ratio is one side length divided by another, and in sine's case, it's the opposite side length divided by the hypotenuse, and side lengths of a triangle cannot be negative. Okay, so I'm going to do the inverse sine of 2 over 5. Okay, and I should get something like 0.4115. Okay, so that is our reference angle. And we will use that to find our angles theta. So we'll have a theta 3 and a theta 4. So for theta 3, we're going to take pi, and we're going to add that reference angle. And so we should end up with something like this, 3.553. And for theta 4, we're going to take 2 pi, and we're going to subtract that reference angle, and we should end up with something like 5.8717. Okay, so you can confirm that with your calculator. Okay, the next one, we've got the tan of x is equal to 0. So for what value or values of x do we have a tan ratio of 0? Now for this, we're just going to draw our basic tan function between 0 and 2 pi. Okay, that's going to be the easiest way for us to figure this out. So we'll call this 2 pi. And so this here is going to be pi. And I'm going to break this up into 4 equal parts because we know that the period of tan is pi, and the significant points still occur in quarter periods. So this is going to be pi over 2, this is pi over 4, this is 3 pi over 4, and so on. And the tan of pi over 2 is undefined. Okay, so we've got a vertical asymptote at pi over 2. We've got another vertical asymptote at 3 pi over 2, which is going to be right here. Okay, we start at a midpoint, we increase to begin. So we've got something like that. So there is our basic tan function between 0 and 2 pi. Okay, so for what value or values of x do we have a tan ratio of 0? Well, 0, pi, and 2 pi, but remember that 2 pi is not in the domain, so our solutions here for x are just 0 and pi. And I'll just put in brackets here, 2 pi is outside domain. Okay, next one. So we've got the secant of x is equal to negative 2 over the square root of 3. The secant of x is equal to negative 2 over the square root of 3. So remember that secant is cosine's reciprocal. So cosine is equal to the adjacent divided by the hypotenuse. So this is going to be equal to the hypotenuse divided by the adjacent. Okay, now cosine is positive in quadrants 1 and 4. So secant is also going to be positive in quadrants 1 and 4, and therefore it's going to be negative in quadrants 2 and 3. Okay, so I'm just going to jot this down here. So we've got an angle in quadrant 2, we've got an angle in quadrant 3 that has a negative secant ratio. Okay, and of course the other thing they share is a reference angle. Okay, so we're going to scroll up to our special triangles, and we're going to look for an angle which has a hypotenuse side length of 2 and adjacent side length of root 3. So hypotenuse 2, adjacent root 3, that is pi over 6. So that is our reference angle. Okay, and we'll use that to find, we'll use that to find theta 2 and theta 3. Okay, so our solution in quadrant 2, we're going to do pi minus the reference angle, so we'll have 5 pi over 6. And in quadrant 3, it's going to be pi plus the reference angle, so 7 pi over 6. Okay, now the next one, number 6, we've got 2 times the cos of x plus 3 is equal to the cos of x plus 2. Let's get the cos of x's onto one side of the equation and the constant terms to the other side, and then we'll go from there. So we've got 2 times the cos of x minus the cos of x is equal to 2 minus 3. So we've got like terms on the left-hand side. We can subtract the coefficients. So we get 2 cos x minus cos x is 1 cos x, or just cos x. And 2 minus 3, we've got negative 1. Okay, so where is the cosine of x equal to negative 1? Again, probably easiest to just draw the graph of our basic cosine function between 0 and 2 pi to solve this. Okay, so we've got 2 pi here, pi over 2, 3 pi over 2, max value of 1, min value of negative 1. We start at a max point, and we decrease to begin. So there's our solution right there. Where's the cosine of x equal to negative 1? At pi. Okay, flip the page. Moving on. So we may need to do some factoring first. Okay, so we're going to solve for values of x between 0 and 2 pi. Now this looks like a trinomial, and we are going to treat it like a hard trinomial. We'll just do a substitution first. Okay, well, let's get rid of those cosines. So I'm just going to say let's let c be equal to the cosine of x. And so we can rewrite the equation as 2c squared minus c minus 1 is equal to 0. And we can factor that as a hard trinomial, and we'll get c minus 1 times 2c plus 1 is equal to 0. And now we can substitute cos x back in for c. So we're going to get the cosine of x minus 1 times 2 times the cosine of x plus 1 is equal to 0. Now we want to make each set of brackets equal to 0, so let's create little mini equations here. So the first mini equation is going to look like this. Cos x minus 1 equals 0. So how do we create 0 out of this? Well, let's take this one step further. The cosine of x is equal to 1. We're looking for that. And I'll skip a step on the next one here. This is going to be, where is the cosine of x equal to negative 1/2? Okay, so we've got to solve each of these equations separately. The cosine of x is equal to 1. You can draw the graph of cosine, or you're probably getting to the point now where you can just close your eyes and picture a basic cosine function. So the solution to this is going to be 0. Okay, 2 pi, the cosine of 2 pi is also 1, but that doesn't count because it's outside the domain. Okay, so there's our first solution for x. The second one, where's the cosine of x equal to negative 1/2? A little bit more work involved here. Negative cosine ratio, so quadrants 2 and 3. We're going to look for the reference angle. So think about your special triangles here. Where do we have an adjacent side length of 1 and a hypotenuse of 2? That's at pi over 3. So that's our reference angle. Oops. Pi over 3. And so we're going to have, we can call it an x2 and an x3. Okay, so the solution, the solution for x in quadrant 2 is going to be pi minus the reference angle, so we're going to get 2 pi over 3. And in quadrant 3, pi plus the reference angle, so we're going to get 4 pi over 3. So there's solution 2 and 3 to that equation. Okay, so number 2 is going to require us to do some factoring as well. So I'm going to substitute sine x out just for s. So I'm going to rewrite 6 sine squared x as 6s squared, and then minus 7s minus 3 is equal to 0. And we're going to factor this. So we'll get 2, and I'll replace s with the sine of x again. So we're going to get 2 times the sine of x minus 3. And this is going to be times 3 times the sine of x plus 1. And this is equal to 0. So our mini equations are going to look like this. So where is the sine of x equal to 3 over 2? And where is the sine of x equal to negative 1 over 3? Okay, so the sine of x is equal to 3 over 2, or 1/2. Let's remember back to the very beginning of this lesson, and remember that the max value of sine is 1. So there's never a value of x that is equal to 3 over 2. So we're going to get no solutions from this little mini equation. No solutions. But we will look at this other one. We don't have a special triangle with side lengths of 1 and 3. So we're going to have to use our calculators here. But this is a negative sine ratio. So we've got solutions in quadrants 3 and 4. And they share this reference angle. And so we're going to find that reference angle by doing the inverse sine of 1 over 3. And we should get something like 0.3398. And so we'll use that to find theta 3 and theta 4. So theta 3, we're doing pi plus that reference angle. We should get 3.4814. And theta 4 is going to be 2 pi minus the reference angle. We're going to get something like this, 5.9434. Okay, and moving along here, we've got cos squared x minus cos x is equal to 0. Those two terms on the left-hand side have a common factor of x. So let's factor, not a common factor of x, a common factor of cos x. So let's factor that out, and we're left with cos x minus 1 inside the brackets. And we'll create little mini equations. So where's the cosine of x equal to 0? And where is the cosine of x equal to 1? And we'll just draw cos x between 0 and 2 pi to help us answer both of these. So it looks something like that. So where is it equal to 0? At pi over 2 and 3 pi over 2. So there's two of our solutions. And then where is it equal to 1? At 0. 0 and 2 pi, but just remember that 2 pi is outside the domain. So we have 3 solutions there. Okay, and flip the page to the last page here. So we've got root 3 times the sine of x times the tan of x minus the sine of x is equal to 0. And what I notice is that those two terms both contain a sine of x. So let's factor that out as a GCF. And if we factor that out, we're left with root 3 times the tan of x minus 1 in brackets. And so our mini equations now look like this. Where is the sine of x equal to 0? And where is the tan of x equal to 1 over the square root of 3? Okay, sine of x equal to 0. Just think about the graph of our basic sine function between 0 and 2 pi. So that's going to be at 0 and pi. So x is equal to 0 and pi. Okay, and then the tan of x equal to 1 over the square root of 3. Let's just draw one of our special triangles here. 1, 2, and root 3. Okay, so opposite of 1, adjacent of root 3. That's this angle up here, which is pi over 6 radians. That is our reference angle. And it's a positive tan ratio, so we've got solutions in quadrants 1 and 3. So in quadrant 1, we've got pi over 6. And in quadrant 3, pi plus the reference angle is going to give us 7 pi over 6. Okay, and the last one here, so we may need to use other algebraic techniques. So let's look at this. 4 sine squared minus 3 is equal to 0. We're looking to isolate x. So let's do this. Sine squared x is equal to 3 over 4. Okay, and if we take the square root of both sides, we're going to get this. The sine of x is equal to plus or minus the square root of 3 over 2. Okay, so that is two sides of one of our special triangles. Okay, so where is the opposite root 3 in the hypotenuse 2? That's at this angle here, pi over 3, which is our reference angle. Now, we've got a sine ratio of the positive square root of 3 over 2 and the negative square root of 3 over 2. Sine is positive in quadrants 1 and 2. It's negative in 3 and 4. So we have 4 different solutions here, 1 in each quadrant. And so we'll use our reference angle to figure out what those solutions are. So we're going to get pi over 3 in quadrant 1, 2 pi over 3 in quadrant 2, 4 pi over 3 in quadrant 3, and 5 pi over 3 in quadrant 4. And that's it for today.